Hold on a second. I think I got the wrong view. I want to be able to say hi to you. Okay. I've been making a lot of statements that sort of hinge around this idea of what's called linear independence. Okay. So let's just go ahead. Let's talk about it first in terms of um, just normal vectors that we know. So if we have a point in two-dimensional space, okay, then we need two coordinates to determine the point. Okay, actually, more generally, is that any, let's now go with vector, in two-dimensional space, okay, can be expressed as a linear combination of two vectors that are what we call now linearly independent. Okay, that's the term that we're going to look to define here. Okay, so now let's just take an example. Let's say I have, this is an easy example, hopefully. Okay, let's say I have the vector, but I'm going to be abstract about it, AB. Okay, then this is equal to A times 1, 0 plus B times 0, 1. Okay, so 1, 0 and 0, 1 are what we call linearly independent. Okay, more generally, any two vectors v1 and v2 are linearly independent okay, if, and only if I should say, although I hate it, let's actually say are linearly independent means that if C1, C2 are both means that C1V1 plus C2V2 equals 0 only if both C1 and C2 equal 0. Okay, so they're linearly independent if and only if. They're linearly dependent okay, if there do exist non-zero C1, C2 with C1, V1 plus C2 V2 equals 0. So now in this case where they're linearly dependent, okay, that means that one of them is a multiple of another. So V1 equals C2 over C1 V1, or we could, I'm sorry, V2 negative, or we could say V2 equals negative C1 over C2 V1, okay? So one of them is a multiple of another. Okay, so the reason that I had to go around this a little bit is because we're actually going to define this term for more than two vectors. Okay, we're going to end up defining this term for n vectors, and then we're going to actually play with that idea. Okay, let's let me go to a new video where we're going to do an example.